Hello everyone, and this is VSAONLINE. So I'm very happy to host two shorter talks today, given by Marco Angioli and Rocco Martino from University of Rome, Sapienza. And so this work is done in collaboration with Antonello Rosado, uh, who is also present here. So without any further delay, please, Marco, as I understand, you will be first presenting, so the floor is yours.
Yes, hello everyone, and thank you, Evgeny, for your introduction and for the invitation. And thank you everyone for joining this session and for your interest in our work. I'm Marco Angioli, and I'm a PhD student at Sapienza University of Rome. And today, together with my colleagues Rocco Martino and Antonello Rosato, we will present an hybrid session consisting of two interconnected talks. The first talk that will be presented by me will introduce HDCB, that is the first exploration of hyperdimensional computing for modeling and solving sequential decision-making in contextual bandit problems. In this talk, we will introduce what a contextual bandit problem is, why it is important, and how the entire decision-making process required by this problem can be mapped into the high-dimensional space and solved using the arithmetic of hyperdimensional computing, looking at all the advantages that HDC can bring in this field. In the second part, instead, we will have a talk by Rocco Martino that will be more hardware-oriented. This talk, in fact, will introduce an open source and general purpose hardware accelerator powered by the first RISC-V instruction set extension in the literature. As we will see, by accelerating the core arithmetic operations of hyperdimensional computing and integrating a dedicated instruction into the RISC-V instruction set architecture and then into the GCC compiler toolchain, this approach has been designed to be adaptable to any learning task. In fact, just by combining the high-level instruction that we provide, anyone can use this accelerator and deploy this accelerator to assess the impact of hardware acceleration on its own algorithm. Now, in general, in this two talk, we will skip over background and basic concepts of hyperdimensional computing, since we think that everyone is already familiar with the topic here. But anyway, obviously, please feel free to interrupt us if you have any doubts or questions. Okay, so let me start with the first talk that, as I said, will be presented by me, and that will be focused on contextual bandit problems. What is a contextual bandit problem? Contextual multi-arm bandits, or simply contextual bandits, are sequential decision-making problems, where we have an agent that interacts with the external environment to learn and adapt in real time through a reward-driven process. At each time step, our agent observes the state of the environment or context and must select which is the best action to take in the given context. Based on the selected option, then the environment provides a reward that is used to update the model parameters and learn in real time. So as you can see, this scenario is pretty similar to our reinforcement learning problem, with the only difference that in contextual bandit tasks, the action taken by the model does not impact on the subsequent context. And thus, the focus is on maximizing the immediate rewards at each time step. Today, many different real-world applications can be actually modeled and solved as a contextual bandit task. For example, these algorithms are used in healthcare to improve treatment allocation and propose personalized dosing strategies, in conversational agent, in hardware reconfiguration, and in many applications in the IoT field. Most importantly, contextual bandits are used in recommendation systems. For example, a website like Microsoft, the New York Times, and Yahoo uses this algorithm in order to provide personalized content delivery. Also, Netflix uses them in order to improve recommendation and learning user preferences over time. For example, in the context of a movie recommendation system, as you can see from the picture in the right side of the slide, The characteristics of the user that is visiting our website represents the context that will be observed by our model. And the goal is to design a model that is capable to learn how to suggest the best movie to the user depending by its own characteristics. Depending by the choice done by the model, then the user will provide a rating, a reward that in the case of movie recommendation can be, for example, a rating that will be used in order to improve the model and learn at each time step. So as you can see, contextual bandit problems can be applied in many different problems, many different real-world problems. But how can we automate and solve these problems? Well, a common state-of-the-art approach in this field involves modeling each different action using dedicated matrices and carrying out ridge regression procedures at each time step to compute the expected reward for each action given the input context. Then the model, as we know, will receive a reward depending by the choice taken by the model that will be used in order to update the model parameters and learn at each time step. Now, the idea behind our approach, referred to as hyperdimensional contextual bandits, is to open this entire processing chain and project the entire action selection process into the high-dimensional space. To do that, as we will see in detail into the next slide, instead of using dedicated matrices, in each DCB, each action is modeled using dedicated hypervectors. These hypervectors are initialized to 0 and then updated at each time step as a function of the received reward to better reflect the quality of the action in the given context. In this way, over time, our goal is to generate representative hypervectors that compactly encapsulate information about the expected quality of each action in the given context. Now, going more in detail, to do that, we adopt the approach depicted in the slide. As you can see, in HDCB, each action is modeled by a dedicated hypervector. This hypervector, as we said, is initialized to 0 and then iteratively updated as a function of the received reward. At each iteration, the model observes a context, the context of the external environment, and maps this context into the high-dimensional space using a record-based encoding technique. In this technique, as probably most of you already know, each feature ID or index of the input feature vector is mapped to a randomly generated base vector. This base vector is then bound to a level vector that is instead derived by discretizing the corresponding feature value and mapping it into the high-dimensional space. This binding creates the feature ID value pairs, which are then aggregated through the bundling operation, resulting into the final encoded hypervector. Then, once we have the encoded context, we can proceed to the action selection phase, in which as we said, we have to search for the best action to suggest in the given context. To do that, we don't use complex ridge regression procedure, as in the literature, but we exploit the mathematical properties of similarity in hyperdimensional computing. In particular, what we do is computing the similarity between the encoded context and the representative hypervector of each action, searching for the closest one. This operation, in fact, will return the action with the highest estimated reward, thanks to how the update process works in HDCB. In fact, after performing our choice and receiving a real valued payoff, this reward will be projected into the high-dimensional space and will be used in order to adjust the representative hypervector of the selected action to better reflect the expected quality of that action. This is done by encoding the reward using a thermometer technique, where the number of active elements increases with the magnitude of the scalar value. Then, after performing the encoding, We bind the result, the encoded reward, with the context hypervector and use this quantity in order to update the representative hypervector of each action. In this way, as we said before, we move the representative hypervector closer to or farther away from the encoded context, depending by the received reward, and thus by the quality of the selected action. So this is the basic formulation of our model that, as you can see, performs maps and performs the entire decision-making process required by contextual bandit problem using just the simple arithmetic of hyperdimensional computing. From observing the context and mapping it into the high-dimensional space, to selecting the action, and finally updating the model as a function of the received reward. Notably, in this process, thanks to the adopted encoding technique and thanks to how the update process works, when observing similar context will lead to similar expectation for the actions. And this allows to effectively exploit the previously collected information and speed up the learning process of the system. Now, in our paper, we detail this approach in 4 different variants, adopting different exploration strategy. Today, I don't want to get into the mathematical details of each approach because it will take too much time, but I just want to mention that when deploying contextual bandit algorithm on a real-world scenario, it's really important to balance the trade-off that we have between exploring less known action and exploiting previously collected information. In fact, as we said many times, we are in an online learning scenario where we don't have an offline training of the model before deployment. Instead, in this case, our model is learning at each time step. And thus, during its execution, it's important to balance these 2 aspects in order to avoid over-exploring or, on the contrary, falling in suboptimal solution. In our work, we detailed the implementation of HDCB integrating 2 different exploration strategies. The first one that you can see listed in the slide as HDCB EPS integrates a simple and straightforward epsilon greedy strategy. In this approach, at each iteration with a probability of epsilon, where epsilon is an hyperparameter of the model, our algorithm will select a random action, exploring the environment. On the contrary, with a probability of 1 minus epsilon, instead, the model will select the action that maximizes the expected reward, successfully exploiting the previously collected knowledge. As you can see, this approach is a really simple and straightforward implementation of an exploration phase and does not introduce any additional computational cost or overhead inside our model. However, as you can imagine, this is not an optimal strategy for exploring because it's strongly dependent by the hyperparameter epsilon. For this reason, in our paper, we also proposed another strategy that you can see denoted in the slide as HDCB ANS, that instead integrates a confidence measure into the expected payoff of each action. So in this case, instead of considering just the expected reward for each action, the quality of an action will be evaluated by the sum of its expected reward and the uncertainty. In this way, as you can understand, the more a certain action will be selected in a given context, the more its uncertainty will decrease, motivating the exploration of other alternatives over time. Then, in addition to these 2 models, in the paper we also introduced 2 other variants, specifically optimized for reducing the computational complexity and memory overhead. But as I said before, today I don't want to explain in detail each of these models because it will require too much time. If you are interested, you can find all the mathematical details behind each of these approaches in our paper. And if you want, you can contact me for any question. What instead I think it's more interesting to look and show today in this webinar is the performance of the proposed approach. And in particular, it will be interesting to analyze which can be the advantages that HDC can bring in the contextual bandit field. Now, to understand that, let's start looking at some of the results that we obtained. In particular, we conducted a series of experiments on various datasets evaluating different key performance metrics. First of all, we examined the online learning capabilities of our model. That is, the capability of the algorithm to improve over time, maximizing the average reward. To verify that, we used the synthetic dataset designed to emulate contextual bandit tasks, and we evaluated our algorithm over 500 time steps. In the slide, you can see the results obtained by the two models that I described before when varying the exploration parameters that are epsilon and alpha for the two models, respectively. As we can see from this plot, the HDCB algorithms are consistently capable of learning and improving over time. In fact, as you can see, the average reward starts at a very low value in the first iteration and then grows, converging towards the unitary value that represents the ideal value. And this means that over time, our approach is actually capable to exploit the previously collected information to learn and improve the decision-making process. So these plots demonstrate that HDCB is actually capable of modeling and solving contextual bandit problems. Additionally, when comparing our models with state-of-the-art approach, we can see from the table in the slide that HDCP consistently achieves competitive or even superior performance on practical benchmark. These results in particular have been computed using the Open Bandit Pipeline framework, that is an open source framework on GitHub, that allows for a standardized and replicable evaluation of contextual bandit algorithm. So as we can see from this table and the previous plot, the HDCB algorithms are able to address contextual bandit problem, learn over time, and achieves competitive performance with the literature. But in addition to the average reward, what can be the advantages that HDC can bring in the field of a contextual bandit problem? Well, the first advantage is related to the convergence speed. Convergence speed is defined as the time, and in particular as the number of time steps that are required by the average reward of the model to converge. When comparing HDCB with traditional linear UCB algorithm from the literature, we can see that our approach that is depicted by solid lines in the plot on the right side of the slide consistently outperform linear UCB in terms of convergence speed. Now, honestly, this is not an unexpected result because we know from the literature that HDC demonstrated many times faster convergence and lower data needs. However, this it's a really important feature for a contextual bandit problem. In fact, we say that we are in an online learning scenario, and thus the time where the model is not trained before, and thus the time that is required to the model to learn and converge towards good decision with choices as a function of the observed context, is very important, especially in applications where evaluating each time step can be time consuming, like for example, a hardware reconfiguration problem, or also critical, like for example, in healthcare application. So we saw that HDCB achieves many advantages, both in terms of average reward and in terms of convergence speed. So a natural thought at this point might be, okay, so we have all of these advantages, but for sure, using hypervectors will require more computational cost or slower execution time. Well, this is not the case for HDCB. In fact, if we analyze the computational complexity of our algorithm and we compare with traditional approaches, we can see that while traditional algorithm shows a computational complexity that grows grows cubically with the size of the context feature vector, HDCB shows a linear dependence by these parameters. And this is because HDCB replaces costly and time-consuming matrix operations, like matrix inversion, with simple instructions between hypervectors, achieving a linear dependence on that parameter. And this it's really important because if we look in the literature, we can see that many different work adopting contextual bandit algorithm uh, requires adopt pre-processing steps in order to reduce the computation, the size of the context and thus the computational complexity of the algorithm, especially in recommendation systems. On the contrary, HDCB is much more scalable from this point of view, and thus it allows to remove this pre-processing step. From this table, we can also see that from the other end, the computational complexity of HDCB is dominated by the size of the hypervector. However, when we look at the robustness that HDCB has as a function of the hypervector size, we can see that when reducing the size of the hypervector from 10,000 to 256, the performance just decreases of about less than 1%. And this confirms that HDCB is robust to the hypervector size and can be a really appealing alternative thanks to its better scalability as a function of the context size. Now, in order to evaluate the impacts of this reduction in computational complexity from a practical point of view, we decided to implement the proposed HDCB algorithm using binary hypervectors on three target platforms: a general purpose CPU, a Raspberry Pi 4, and an embedded RISC-V core. In the slide, you can see the results obtained in terms of execution time varying the context feature vector size. Now, independently by the absolute values of execution time that obviously depends by by the characteristics of the target platform, by the computational power of the target platform, what we can see is that, as theoretically expected, HDCB achieves a linear dependence in terms of execution time as a function of the context feature vector size. Additionally, we can see that when the context feature vector size grows, HDCB becomes faster than traditional models. However, the real advantage that using the HDCB has lies in its inherent highly parallel operations. In fact, we know from the literature that thanks to the distributed and holographic nature of hyperdimensional computing, all the operations can be performed in parallel on each element of the hypervector. So in order to prove that and evaluate from a practical point of view the benefit of this inherent parallelism, we evaluated the impact of hardware acceleration on different contextual bandit algorithms. In particular, we implemented the traditional linear UCB algorithm on the clessidrat core and accelerated it using a vector accelerator. Then we compared its execution time with the one obtained by the proposed HDCB algorithm accelerated using the HDCU accelerator that will be introduced and explained by Rocco in the next talk. I want to say that the HDCU accelerator, as will be explained, is not an accelerator, an application-specific accelerator designed for this task. Instead, as will be explained, this is a general-purpose accelerator for hyperdimensional computing. And here, by employing it for our algorithm, we demonstrated its adaptability. As you can see from the plot on the right side of the slide, when adopting hardware acceleration, HDCB achieves up to 200 times speed up over the software execution. And in particular, when compared to traditional algorithms, also accelerated in hardware, HDCB outperforms this algorithm by an impressive value ranging from 3.2 to 30 times as the context feature vector size increase. So, to summarize, in this work, we demonstrated how hyperdimensional computing can be adopted in order to model and solve contextual bandit problem for the first time in the literature. We detailed the model in 4 different variants, and we deeply analyzed the performance of HDCB and the advantages that this can bring in the field of contextual bandit problem. Overall, we can say this approach achieves competitive performance, faster convergence speed, better scalability, lower computational complexity, and it is a perfect candidate for hardware acceleration. Thank you very much for your attention, and if you have any question, I'm more than happy to answer.
Marco, thank you very much. It's really cool.
Thank you.
Yes, really fresh uh, approach to reinforcement learning. So I really appreciate it. Questions from the audience, please unmute and ask Marco. So we take a brief Q&A session now.
Marco, could you comment on? You said you're using linear hypervectors to do the weighting. How, the granularity that you've got there depends on the hypervector dimension.
Yeah.
How did you take that into account?
You mean which size I used?
Yeah,
Okay, yeah. As you can see from the previous slide, okay, first of all the results in terms of performance, meaning these ones on the average reward, the comparisons with the state-of-the-art approaches, and also the ones on the execution time, have been obtained by selecting an hypervector size of 1000 element. However, in this slide, you can see the impact of hardware of different hypervector size on the performance of the model. From this plot, we can see that for models like HDCB apps and HDCB uncertainty, that are the ones that I presented, that I described more in detail today, the impact of hypervector size it's really low, meaning that the model it's highly robust. In fact, on the previous test on synthetic datasets, we demonstrated that we can reduce the size up to 256 elements by losing just about 1% of average reward. From this plot, you can also see that instead there is a model, that is the green one, that is much more sensible to the hypervector size. And that is because this model is the one that I mentioned is optimized for the memory overhead. In fact, if you are interested and if you look in the paper, you can see that this model replaces, instead of using dedicated hypervectors for each action, leverages the properties of permutation operation in order to compactly encapsulate the information. And thus, for this reason, since we are using less hypervectors, then at this point, the size of the hypervector becomes a much more important parameter.
great. Thanks very much. Thanks.
There is one question in the chat from Madison. Is it possible to decode the learned components of the model into something symbolic? That is, see a symbolic representation of the stuff it learned.
Okay, let me say that as I said, for how the encoding and update process works, when we observe similar context, we will have similar expectation of the models. So, in a certain sense, when we encounter similar input vectors, we will have similar action, and so we can understand which are the choices of the model. Instead, if we intend that we want to really perform a decoding, meaning that we want to come back to the original component of the hypervectors, that would be a little bit more complex. But I think that maybe this can be done because the operations that are required are simple. For example, here in the case of the encoding, we just use binding and bundling. So it's not too complex to perform decoding, clean up memory, let's say, and search for the component. Uh, yeah, especially when implementing this approach with binary hypervectors, like we did, for example, for embedded system, I think that this could be done. When instead we adopt other approaches, like the one that I denoted here as HDCB uncertainty tree, that is the one that, as I said before, uses permutation, I think that in that case it will be more complex. I don't know if this replied to the answer.
Thank you.
Thank you.
I have a question or maybe a comment to your previous reply to Graham's questions.
Yeah.
About the dimensionality. I think what you observe, I mean, as what you regard as robustness, it somehow needs to be complemented with the information about the number of items you include in the context, because it is there where the dimensionality plays a critical role. So to me, I mean, this figure means that maybe the number of features in your context is relatively small compared to any dimensionality that you can consider. Is
Yeah.
it true?
Yeah. That's true for sure. And in particular, these plots have been obtained by using the same dimensionality that we used inside this.
So you say that it's like this n, is it number of things you have in the context? So in that table, this n, 10
No,
features.
in that table, what impacts the capacity? I mean, what is encoded into the high-dimensional space when we encode the context is depending by D.
So it's either 5 items or 10 items.
Well, in that case, for these plots, the D was equal to 20 because 20 is the value that we used also for these
Okay.
plots. I removed the caption, but anyway, if you go in the paper, there is 20.
Yeah.
And yeah, for sure, it depends by the context because this is what we do. We perform the encoding, and the encoding depends by the size of the input context, that is D. So the higher D, the more the hypervectors and the items that we are bundling together.
Absolutely.
And yeah, instead n represents the number of actions inside the problem. So the number of alternatives from which we want to find the optimal one. And in the two first approaches inside this slide, each action is modeled by dedicated hypervectors. So in these approaches, I don't think that the number of action will be a problem. Instead, when we use permutation to compactly represent this concept, and we don't use anymore one dedicated hypervector for each action, then I think that also the number of action could could represent a problem for capacity. So I think that you should find the best alternatives for depending by the application.
Yeah.
And that's the idea for which that we have for which that motivated us to propose different models. For example, the last one is less performant, but it requires much more memory overhead.
Okay.
So you can find the best trade-off for your application.
Okay, Marco, thank you once again. So we probably will return with more questions towards the end. So now I think it's time to switch to Rocco. So and
Yes.
listen for the second part of talk.
Let me share my screen. Okay, are you able to see my
Yes.
screen?
Mm-hmm.
Okay. So thank you, Marco, for the introduction, and thank you, Evgeny, for organizing the session, and thank you all for joining us. My name is Rocco Martino, and I'm a first-year PhD student in electronic engineering at Sapienza University of Rome. As Marco mentioned earlier, the second part of the talk will be more hardware focused. I will introduce HDCU, which is an open source general purpose hardware accelerator for hyperdimensional computing, powered by a RISC-V instruction set extension designed specifically for hyperdimensional computing. Okay, Okay. So one of the most impressive aspects of hyperdimensional computing is its inherent parallelism. And thanks to the distributed way in which information is stored in hypervectors, every fundamental hyperdimensional computing operation can run in parallel on individual vector elements. This property has been widely exploited in the literature, leading to the development of several highly efficient hardware accelerators in various application domains. But by reading literature, we notice that all the accelerator had some common limitation. None of the existing hardware accelerators can be easily repurposed for learning tasks different from the one they were originally designed for. The hardware is tightly coupled to the data set and often accelerate only composite operations such as encoding or inference. And the hardware is often built to work with the fixed length and type hypervector. And so we asked ourselves, since hyperdimensional computing is a computing paradigm, how can we design a general purpose accelerator that overcomes this limitation and can be used in different scenarios? So this is exactly what we set out to achieve with our work. We design a highly flexible and reconfigurable hardware accelerator that optimizes the execution time of hyperdimensional computing arithmetic, and it's simply usable, simplifying algorithm prototyping and enabling developers to quickly assess the impact of the hardware accelerator on their application without the need for custom design. Okay, oops, my mouse doesn't work. Okay. For demonstrating purposes, the accelerator has been integrated into the Clessidra T03 RISC-V core, and the accelerator works in parallel with the execution and load store unit, acting like a coprocessor, and it is controlled by dedicated hardware instruction. In fact, our approach leverages one of the key strengths of the RISC-V instruction set architecture, its open source nature. And we design a custom RISC-V instruction set extension, introducing a custom instruction that are listed in the table on the slide that cover all the arithmetic operation of the hyperdimensional computing. These instructions are integrated into the GCC compiler toolchain and easily accessible for high-level programming as simple intrinsic C function. And this modular approach allows programmers to implement any hyperdimensional computing algorithm by appropriately combining this instruction. Now, for each of these instructions, the accelerators includes a specialized and highly optimized functional units in hardware for a total of 6 different units, as we can see on the right side of the slide. The hardware parallelism of these units can be set at synthesis time, balancing execution time and hardware requirements. Then, whatever the adopted hardware parallelism is, the accelerator works using hardware loops. This means that once an instruction belonging to the designed instruction set extension is patched, the accelerator will keep the required functional unit busy until the entire hypervector is processed, removing the need for continuously fetching the same instruction. For instance, when processing a 10,000 element hypervector with an hardware with an hardware parallelism of 100, the accelerator keep processing data for 10 consecutive clock cycles, fetching the instruction only once. And this is a major advantage because it allows processing long hypervectors in a subsequent clock cycle without keeping the main core busy and efficiently handling hypervectors of different sizes with the same hardware. Additionally, a key feature of this design is the possibility to selectively enable or disable each functional unit. For instance, if our application does not require the permutation operation and we want to deploy the accelerator in a resource-constrained system, we can choose to disable the permutation unit, saving hardware resource. And this flexibility allows to optimize hardware utilization tailored to different workloads. Now, to avoiding incurring in bottleneck caused by the transfer of hypervectors from the main memory to the functional unit and vice versa, our architectures integrates local memory denoted as scratchpad memory (SPM). All the computation are performed on hypervectors stored in the local memories, and only at the end the result can be transferred back to the main memory if required. So the transfer from and to the main memory is controlled by two dedicated instructions that you can see here on the slide. One is the hvmem load, and the other is the hvmem store. So the number and the size of scratchpad memories are two other tunable parameters that can be set at synthesis time to balance computational efficiency and resource usage. The table that we can see in the slide summarizes all the levels of configurability of our accelerator, and in particular the size of the hypervectors and the number of classes to be compared during associative search can be set at runtime through a dedicated current status register without the need to resynthesize the entire hardware architecture. And this configuration step is performed only once at the beginning of the C program, and enables the accelerator to execute hardware loops. So the dual flexibility coming from hardware configuration and software programmability sets this work apart from application-specific solution in the literature, and offer a unique and versatile accelerator which is adaptable to a wide range of application and learning tasks. In this regard, I'd like to show you an example of how the record-based encoding of a feature vector is executed using our custom RISC-V instruction. Let's start with a quick recap. Looking at the diagram on the left, we see that X is a vector of real numbers, just like any pattern in a typical dataset, and each feature value is quantized and mapped to a corresponding level vectors, and each level vector is then bounded by its associated base vector, and finally all the information is condensed into a single hypervector through the bundling operation. Now, on the right side, we have a C-like pseudocode illustrating the implementation of this process using a custom instruction. First, we assume that both base vectors and level vectors have already been generated. And the process begins by loading them from clepsydra mains memory into the scratchpad memory using the appropriate instruction. Once the data is in place, we configure the accelerator by communicating the hypervector size through the CSR register, the current status register. Now, with the setup complete, the encoding process begins. Inside a for loop, the binding operation is performed between each base vector and its corresponding level vector, with the results accumulated into the scratchpad memory, which is called the scratchpad memory D. And at each iteration, the result is accumulated using the HV bundle instruction, and the result is stored all in the same scratchpad memory. After performing the bundling, to bring the result back in binary domain, we use the HV clip instruction that applies a simply majority rule. And this approach demonstrates how record-based encoding can be efficiently executed using our RISC-V accelerator, significantly enhancing performance compared to a purely software-based implementation. Now, let's now move on the hardware implementation on FPGA. To evaluate the impact of different configuration of our design, we choose to use high-performance FPGA, which is the Xilinx Zinc UltraScale Plus. The table in the top right corner presents the hardware requirements of the Clessidra core with our accelerator in what we can consider a minimal configuration with an hardware parallelism of 32 elements processed per clock cycle. And the core occupies around 4,000 lookup table. Meanwhile, accelerator requires just around 1,000. In the last two rows of the table, we can see the hardware requirements of the memory modules and their interfaces. The table in the bottom right corner shows how the hardware requirements scale with different level of parallelism. And this table demonstrates what I mentioned earlier. The hardware parallelism allows us to establish a trade-off between hardware resource usage and computational performance, and find the best configuration according to the application needs. For example, if we want to deploy the accelerator to optimize the learning process of our algorithm on a high-level FPGA, we would be mainly interested in having a higher hardware parallelism and thus a lower execution time. On the contrary, if we want to perform inference on a resource-constrained and low-power FPGA, we can choose a lower hardware parallelism and eventually disable not required functional units. Now, let's look at some results. First, let's clarify that we measured the performance of our accelerator using the speed-up factor. This factor is computed as the ratio between the number of clock cycles required by Clessidra to execute an HTC operation purely in software, and the number of clock cycles required when the same operation is performed using our accelerator. On the right side, we have 6 different graphs, each corresponding to one of the functional units implemented in the accelerator. And now let's take a closer look to one of the graphs to fully understand the impact of our design. The speed up factor was computed while varying both the hardware size and the level of parallelism. On the x-axis, we report the HV size in bits, while the different colored curves represent the various levels of parallelism. Of course, I selected one of the most significant graphs, and this graph represents the bundling operation, and I'd like to highlight its highly predictable behavior. As expected, for small hypervector size, the speed-up factor remains relatively low. And this means that the number of clock cycles required by Clessidra in software is comparable to the number of cycles required when using the accelerator. However, as the hypervector size increases, the speed-up factor grows rapidly. And it's remarkable that for bundling with the most powerful configuration, we achieve a speed up factor of 2600. And this means that the bundling operation is performed 2600 times faster than it would be if executed purely in software on Clessidra. Now, let's see how the accelerator perform on real-world dataset. We test two examples, a spatial classification problem, sorry, and a temporal one. In both cases, the accelerator significantly reduced the time it takes to encode data, especially when those encodings rely heavily on repeated bundling and permutation operation. And with the cardio dataset, we achieve a speed up that is ranging from 13 to 2147. Then moving to the EMG dataset, where the encoding involves some more complex temporal sequences, the speed up becomes even more impressive, ranging from 13 to 2147. Oh, sorry. In short, we can say that these results confirm not only the raw efficiency our approach can offer, but also its ability to adapt to a wide range of tasks, demonstrating its flexibility and scalability across different types of data. Okay, thank you for your attention, and if you have question, we can talk.
Rocco, thank you very much for your part of the talk. Super interesting in my ears. So let's see what questions we have in the audience. Oh. I'm actually wondering if you did this comparison, or maybe, I mean, that's not totally fair even to suggest, but in the previous talk, so Marco was talking about changing reach regression to vector operations. I mean, it would be interesting to see so how much, or do you have any feeling, so how much speed you would gain, I mean, with your acceleration? So, for example, matrix operations versus vector operations that's on hypervectors. I don't know if I express myself clearly.
Maybe.
I mean, you highlighted in your graphs, you highlighted kind of speed up compared to software realization of this operation, right? What would be interesting to see kind of, I mean, speed gain compared to, using other benchmarks for solving same task.
Yeah,
Maybe
yeah, for sure. This could be an interesting test, and maybe
maybe you mean evaluating and comparing the performance that we will get by using a vector accelerator versus our accelerator. This is what you mean?
Vector accelerator versus what do you mean by your accelerator? You mean some standard
Yeah.
accelerator? Yeah, so absolutely. So
Yeah, I think that if we do this comparison, the main advantage that you will see is related to, for example, operations like bundling or associative search. Because just for doing an example, maybe when you deal with bundling, inside bundling, in our approach, you can specify the number of bits of each hypervector elements. So which is the precision that you want to maintain during computation. this can be specified at synthesis time. So let's say that you specify that you want to operate on 4 bits element, then all the hardware will be synthesized specifically to process 4 bits at a time. So your 32-bit word, for example, will be divided into many words of 4 bits and processed in parallel. So in all the operations where you can have I mean, the biggest advantage you will find on operations where you have specific task where a specific hardware can bring more advantage.
Yeah, I think yes, I think you answered my question.
So I would think that if you adopt a general vector accelerator, you will find something in between the software execution and our approach. Because this is still an hardware accelerator, but it's not specific to the task.
Yes.
Yes, so I've got a question. Is your binding operation an XOR binding?
Yeah, is XOR binding because uh, for the first approach that we had to our accelerator is the binary sputter code approach.
Yeah.
So for the moment actual state, the accelerator just accelerate hypervector operation, HDC operation with the binary hypervector. So yes, it's XOR operation.
Right, and you're Hamming similarity
Yeah.
computation, but you're only doing that between pairs of vectors. Can you accelerate doing it against for a cleanup memory, having many vectors that you want to do the Hamming similarity against? Have you thought about making a very efficient cleanup memory?
Yeah, you can do this by using the associative search instruction.
Right.
Associative search is just as the similarity, but with the difference that you can specify in a current status register, so you can specify in a register by software, you can specify how many hypervector you want to compare to. And so automatically the hardware accelerator will compare your input hypervectors with n hypervectors that are in a memory that you specify as a parameter of the instruction. And so this can be used both for associative search, but also for cleanup memory, for example, where you want to find the most similar one.
Okay. And have you thought about implementing a resonator network?
Yeah, we are working on it because we are working on extending the accelerator on complex number.
Right.
And so, yeah, in that case, it would be necessary. And so we are working on doing that.
Okay, thanks. Interesting.
Thank you very much.
Tony.
Yeah, very, very interesting stuff. And along the similar line of questioning, thinking about making like a cleanup memory, just a large associative memory. How much memory, like how many hypervectors could be stored on one of these FTPA chips if you wanted to do something like that? So it worked in parallel, comparing across a large set. Could you store thousands or millions of hypervectors, or what's the
Yeah, this is just depending by what you want to do and by the capabilities of your FPGA. Because as Rocco explained before, all inside the accelerator can be configured at synthesis time. So we give to the user as much freedom as possible because we want this accelerator to be open source and usable by everyone. So it depends by you. You can specify the size of each memory at synthesis time. And so if you want to deploy the accelerator on a very small FPGA, you will optimize as much as possible. If you're not interested in that, you can, for example, if you want to perform a training, in that case, instead you want just to have the best performance as possible, and then you can put very big memory, very high hardware parallelism, as you prefer.
And yeah, I don't know much about what the capacity of the FTPAs are. Is it how big can they get? Like how many bits
It
can they
depends
store?
on the FPGA, and usually you can implement something like, for example, in a small FPGA, something like 600 kilobytes, something like that. And obviously, if if you buy an expensive FPGA, maybe this value can grows up. And
At 20,000 FPGA, then you can have a lot of money.
Right, you mean $20,000? You're when
Yeah,
yeah,
exactly.
yeah, yeah, yeah. And how hard are they to play around with and program?
it's
You
it's
you you mean with the accelerator or with FPGA?
Um, to get something running, to like do what you've done, is that a relatively simple thing, or do you need a lot of equipment?
No. It's really simple. You can just take our accelerator and the core from GitHub because both of them are open source.
Yeah.
And then you can both simulate them. So you can use software that simulate the hardware execution to verify if everything works. If you're just interested, for example, to looking at the speed up in terms of clock cycle, you can simulate. Or otherwise, you can just download the software to synthesize on FPGA and put the hardware design inside the software, that is, for example, Vivado, and select your FPGA and click implementation and wait for deploying the accelerator on FPGA.
Um, I have again question because I'm not hardware person, but I know what FPGA is, but can this accelerator somehow help in porting or implementing HDC operations on embedded devices, or are there any FPGAs so that are kind of classified as embedded stuff?
Yeah, for sure. Because when you deal with embedded application, and for example, you have constraints on the power or execution time or whatever it is, then that's exactly the application scenario where you want to have a dedicated implementation, an application specific hardware, because in that way, always will be as much optimized as possible. And so you will consume lower power, etc. So it is also possible to, I mean, this is using FPGA also is really useful for embedded application. Then the terms embedded depends by the
Mm.
FPGA that you buy.
Of course, of
If
course.
you can buy also a $30 FPGA and deploy our accelerator. We did that, and you select the minimum hardware parallelism as possible, but still it is an accelerator dedicated to hyperdimensional computing.
And maybe, other comment, again, not very uh, thought through idea, but coming back to your talk, Marco. So, did you try? I mean, after you train the system, so on whatever dimensionality you choose, um, did you try, for example, to down project the resulting action vectors to some small dimensions and see the effect?
Okay, not yet because
Maybe
I
that
know.
you can probably try and see.
Yeah, but the problem is that I know that this approach is really useful when you have, for example, classification problem or something like that. But in our case, we are in an online learning scenario, so we have not a previous phase in which we train the model.
Yeah. In
S-
online, yes, I
So
understand.
maybe a solution could be to dynamically, I don't know, do something dynamic in a
Yeah.
dynamic way. reduce complexity. I mean, maybe for example, every 1,000 steps, you stop the execution, you do some reduction, and then you go on. I don't know.
Because I mean, I can imagine that in the real settings, you have two phases. I mean, the adaptation phase and then a kind of search phase. I mean, most of the time, the convergent system is only used to determine action. So, I mean, for fast operations, you can have a second copy.
Yeah, 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 that's true. That's true. Yeah, this could be a really interesting approach, especially because, as we saw, one of the advantages is that also the execution time.
Yeah, absolutely.
So if we are able to do something like that, we can further improve the
Mm,
advantages that we have.
mm,
And also, I didn't show for a question of time, but if you go in our paper, you can see that we also have less memory overhead
mhm.
compared to traditional algorithm.
Yeah,
And
but of
that's,
course, I mean, you don't need matrices.
yeah, yeah, yeah. So one scales cubically, and our approach is linear.
Okay. So let me check if people have questions online.
Yeah, yeah. One last question. So you said you had some papers on this accelerator and some GitHub resources.
Yes.
Is that right? Yeah, I didn't find, I was Googling at HDCU plus your names before and I couldn't find anything. So
Can you put link to chat, uh,
yeah.
guys,
Yeah,
now?
yeah, for sure. Because it is on preprint, so maybe that's why.
And also, I would be interested to read the first paper that you, Marco, presented.
Sure, sure. Now I will share but the links. Okay.
Oh, there is another question here. So before we forget, so from Madison, how do you see pure digital HGC accelerators comparing against HGC platforms using novel materials like memristors, etc.? Are they likely to offer significant improvements over this approach, or in being included somehow?
Okay. Honestly, we are not expert of this type of. I know that a very important side of the research in this field involves memory stores, in-memory computing, and neuromorphic computing, and all this stuff. Uh, Honestly, we work on pure digital
That's
design.
okay. That's okay.
So I don't know exactly how to answer, but for sure, any optimization that you can perform is will improve the performance that you have. Now, the point I think that the point in this regard is to finding the optimal trade-off for an application because adopting memory store, etc., it can be really useful and improve the performance, but it can be complex because if you are a researcher and if you want just to accelerate your algorithm, you have an FPGA, you don't have memory store in usually.
Fair enough. Yes.
Thanks a lot.
Thanks.
And also, what I honestly I like, and that's why I also want to look deeper into your papers, is, I mean, really the scalability, as you say. So it's really limited by the proper characteristics of FPGAs, and because whatever neuromorphic implementations I've seen, so in terms of dimensionalities and a number of vectors to be handled. So it's, I don't know, it appears to be somehow limited. Okay, but I mean, would you, if, how do we do with the links? Are you planning
Yeah,
to
yeah,
put
yeah.
them
I'm sending. I'm
online?
sending. Just one second.
Yeah, no, no, but I mean, it's okay. So actually, what I will do, I stop recording. Thank you very much all for being
Thank
with
you.
us today.
Thank you.
And
Thank
thank
you.
you, Rocco and Marco, for the great talk. Absolutely.
Thank you.
Next talk will be postponed. So I will send an announcement separately. So stay tuned. So I stop the recording now.